right. So now we're actually starting on the book material. We're going over section 1.1 and 1.2 today. The point of the first two sections here, it's basically preliminary stuff that you should have already come into contact with just through the course of your algebra courses, for the most part. So first off, 1.1 is a great section for you guys to actually read and go through because it's just a quick review of a bunch of things. It's a great section for you to quickly find things that you're struggling with and know the holes that you need to plug in for yourself. So if any of this stuff seems weird that we quickly cover today, between now and next week, it would be good to go, I don't know, watch some YouTube videos or something on that specifically, fill in those gaps for you. So preliminary stuff, quickly laying the foundations for what you should have seen in previous classes. First two sections, focusing on functions, and then all we'll do next week is another trick review, how the book does it. And then the week after that, we'll start on calculus proper material. Okay, so functions. I already gave you the way I like to introduce functions last week and the definition I liked last week. Now I'm just going to follow the book. So your book's definition. A function f from a set D to a set Y is a unique rule that assigns is a rule that assigns a unique element f of x in Y to each element x in D. We call D, that set, the domain, and we call the set of all your f sub x's the range. So get a picture really quick here. Let's say we got some function. Here's 1, here's 2, here's A, here's B, and my function assigns 1 to A and it assigns 2 to A. Here's my D, here's my Y. So my function is sending 1 to A and it's sending 2 to A. Is that a function?
Yes.
Yes, we sent everything in D to a unique thing in Y.
What's Y again?
Y, it's just a set.
Just set.
Now, what is our domain?
1 and 2.
The set containing 1 and 2. Our domain is the set containing 1 and 2. What is our range?
The set containing A and B.
The set containing just A is our range. You do not have to use the entire set Y.
Why?
By definition.
Oh. Yeah.
Okay.
So you do not have to use all of Y. And we'll see a bunch of functions that don't use all the Y that we send them to. Okay? So, say this one more time. A function f from a set D to a set Y is a rule that assigns a unique element f of x and y to each element x in D. So we have to assign something to each element in D. So we always use up all of D. We do not always use up all of Y.
Yeah.
Make sense?
Yeah, that makes sense.
We call D the domain, and we call the set of all f sub x's the range. Y is not the range. The set of all the values out of Y that we use is the range. More vocabulary. If Y is equal to some function in terms of x, we call x the independent variable, and we call y the dependent variable. The value of y depends upon x for its value. You've got to give me an x for me to determine what a y is. We use these types of functions to model all sorts of things. One of the examples the author gives in your book is thinking about the boiling point of water as a function of your altitude. The higher up you are, the lower the boiling point of water is. In that case, your altitude would be your independent variable, and your boiling point of water would be your dependent variable. What's the boiling point of water? It depends upon your altitude. Your altitude does not depend upon the boiling point of water. We don't think about it that way.
Yeah.
Okay. So, independent and dependent variable. Y depends upon x for its value.
Yes.
X is independent of y. All right. Now, we don't always tell you exactly what the function's domain is. We don't make that explicit for you all the time. And so there's this notion of what we call the natural domain. The natural domain of a function is all the numbers you can plug into that function and still have it work. All the numbers you can plug into the function without breaking it. if your domain is not explicitly given to you, it is just understood, it is just assumed that it's using what we call the natural domain. So the natural domain, that's the set of all x, such that f of x is still a real number. The natural domain is the set of all your x's, such that f of x is in the real numbers. Let's go over some concrete examples. So I'm going to give you the function. You're going to tell me its domain and its range. With me? Since none of these functions, I didn't tell you what the domain was explicitly with any of these functions, so we're assuming the natural domain. So it's going to be all the values we can plug into the function without breaking the function. What is all the values I can plug in for x here without breaking my function?
Squared numbers.
I can plug in any number. Tell me the number that I can't take the square of.
Oh yeah, that's right.
I can square any number and still get a number. So in this case, the domain is all real numbers. So you can write that with this R for all real numbers, or you can use interval notation. It's all the numbers from negative infinity to infinity,
But
however you want to write it.
Real numbers are not decimals then.
Real numbers are what you think of when you think of a number. Is a decimal number a number?
Yes.
Then it's a real number. Do you know what a complex number is?
What's a complex?
Fantastic. So you don't know what a complex number is. So everything you think of as a number is what we mean by a real number.
Is complex number that number?
It has imaginary parts.
Oh yeah.
So if it doesn't have any imaginary parts, it's a real number. So decimal number is real number. Square root of 2, real number. Pi, real number. Anything that's a number is a real number. Okay, what's the range now on this function? What are all the values I can possibly get to come out of this function? What are all the possible values of y?
All positive real numbers.
All the positive real numbers, right?
And 0.
And 0. So it's everything from 0 up to infinity, including 0. How do you get 0 to come out?
Plus 0.
Plug 0 in and 0 comes out.
Yeah.
Okay, next one. What are all the values I can plug into this function without breaking it?
All of the
Any
positive real numbers.
All the positives?
Except for 0.
All real numbers except for 0. So in general, there's only two things you have to watch out for. The two things we can't do.
0.
Number 1, we can't divide by 0. Number 2, we can't take the square roots of negative numbers. Those are the two things we can't do. That's pretty much the only two ways you can break a real valued function.
You can't square a
all we
negative
care about.
number.
Huh?
You can't square a negative number.
You can square a negative number. You can't take the square root of a negative number. What times what? Think about this. Think about taking the square root of negative 2.
Okay.
Or let's say negative 4. One that's easy for us to think about. That's saying what number, when I multiply it by itself, gives me negative 4?
Negative 2 times 2.
Negative 2. What's negative 2 squared?
1, negative 1.
What's negative 2 times negative 2?
Oh, positive 1.
Negative 2 times negative 2.
Oh, positive 4.
Positive 4. It didn't give me negative 4. What number can I take such that when I multiply it by itself, I get negative 4?
It's impossible.
It's impossible. Because 2 times 2 gives me positive 4, and negative 2 times negative 2 gives me positive 4.
Yeah.
None of them give me negative 4. So we can't take square roots of negative numbers, and we can't divide by 0. Those are pretty much the only way you break these functions. So what can I plug into this function and not break it?
Everything but 0.
Everything except 0. What are all the values of x's I can have? Everything but 0. So that is negative infinity to infinity, union with, or not to infinity. That's everything from negative infinity to 0, not including 0, union with 0 up to infinity. You good with that notation?
Are joint.
Union means take everything that shows up in either set.
Okay.
Okay, what is the domain of this function, or what's the range of this function? What are all the possible y values I can get out of here?
Any real number except for 0.
Any number except for 0. What can I plug in for x to get 2 to come out? 1/2. If I plug in 1/2 for x, this is just a reciprocal of this. So what's a reciprocal of 2? 1/2. If I plug in 1/2 here, 2 comes out. So pick any number you want to come out. Its reciprocal is what you plug in to get that number out. So the only number you can't get out is 0. Because what's the reciprocal of 0? 1/0, which is undefined.
Yeah, that's it.
So 0 is the only number without a reciprocal. So once again, it's everything from negative infinity to 0, union with everything from 0 to infinity. So same domain and same range on there. Next one. Square root function. What's everything I can plug in?
All the positive numbers.
All the positive real numbers?
Yeah. That makes sense.
All the positive real numbers?
And
Except
zero.
for 0.
And including 0.
Is that?
You can
What's the square root of 0? What times what gives me 0?
0.
0. 0 is its own square root.
Yeah.
So we can plug in everything from 0 to infinity, including 0. All right, what can we get to come out of this function?
All the positive real numbers, including 0.
Right, I can't take the square root of a number and get a negative out. So I can't get any negative numbers.
Yeah. So
So-
all positive.
Once again, all the positives, including 0. So 0 to infinity. So once again, same domain, same range.
Yeah.
It's just an accident. These things don't have to have the same domain, same range. All right, next one. What are all the numbers I can plug in here without breaking it?
All the positive real numbers.
Positive.
numbers.
Plug
All
5
the
in.
positive real numbers.
5.
What's 4 minus 5?
1. So
Negative 1. What's the square root of negative 1?
Doesn't work.
Doesn't work.
So all
So
positive.
you can't plug in 5.
All positive real numbers over 4.
5 is a positive real number over 4.
Oh, sorry.
So why isn't it 1? Why is it negative 1?
If I plug in 5 for x, what's 4 minus 5?
Oh, all positive real numbers below 4.
Negative 1.
How is it negative? It's 1. Positive 5.
Just
You're plugging in for x.
all numbers minus.
Yeah.
So 4 minus 5.
All numbers below 4.
All numbers, all
What are you talking about? You're seeing something
real
weird.
numbers.
We're looking at 4 minus x.
Yes.
Plug in 5 for x. That's 4 minus 5 equals.
Oh yeah. I put
It's
this
all real
You're,
numbers.
yeah, you keep changing the sign. No, we're just plugging in for x.
All real numbers below.
That makes sense.
Less than 4. All real numbers less than 4. Including 4.
Alright. So you can't plug in 5. Can you plug in 10?
No.
No. Can you plug in 100?
No. So it,
What about if you plug in 0?
that would work.
That works.
4 minus 0 is 4, square root of 4 2. That works.
So anything below 4.
Anything below 4. Can I plug in 4?
Yes.
Yes.
Yeah.
Anything
That's
below
0.
So
Yeah,
anything
that's
4 or less works.
Yeah.
So we can plug in everything from negative infinity up to and including 4. Alright, what can we get to come out of this function?
All
0
positive.
on up.
All positive.
Can you get
numbers,
negatives?
Including 0.
0
You
on up.
can't get negatives out of the square
Yeah.
root.
So it's 0 on up.
0 on up.
Yeah. That makes sense.
0 is the smallest thing we can get out there. We get 0 out when we put 4 in.
Yeah.
And as we put more negative values into the function, we get bigger values coming out of the function. If I put 104, or negative 100, if I put negative 96 in here, 4 minus negative 96 is 4 plus 96 is 100. We get 10 coming out the other end.
Yeah.
Okay. Next. What are all the numbers I can plug in here?
They should be the same thing.
Well, let's test one. Plug in 2. What's 2 squared?
2 squared
Negative 4.
is
2 squared is 4. 1 minus 4 is
3.
negative 3.
Negative 3.
Can you take the square root of negative 3?
No.
No.
So 2 doesn't work. Okay, let's try negative 2. What's negative 2 squared?
It's 4.
4.
Positive 4. What's 1 minus 4?
Negative 3.
Negative 3. Okay, that broke it too. Can't plug in 2, can't plug in negative 2.
Imaginary numbers.
No,
Anything from
we're
0
only
to
dealing with
1.
real numbers. Huh?
Anything from 0 to 1.
Anything from 0 to 1.
Oh.
Can I plug 0 in here?
Yes.
Yes.
Can I plug 1 in here?
Yes.
Yeah?
Yeah. What's 1 squared is
1 squared is 1.
1.
1 minus 1 is?
Oh, yeah, 0.
0.
So it's 0 and 1. Yeah, that makes sense.
Square root of 0 is?
0.
0, so that works. Okay, what about negative 1? What's negative 1 squared?
1.
1. What's 1 minus 1?
2.
0.
0.
Oh, yeah.
He's telling the truth. And
What's the square root of 0?
0.
So it's 1, 2, negative 1.
So it's all the numbers from negative 1 to 1. Or all the numbers we can plug in there without breaking it.
Yeah.
Make sense? Alright, what are all the numbers we can get to come out of this thing?
0.
0? We can get 0 to come out, okay.
Is that it? That's it.
That's the only number you can get to come out?
0 to 1.
0.
Can we get 1 to come out?
How do you get 1?
Plug in 0 for x. What's 1 minus 0?
Yeah. You can get 1.
So you can get everything from 0 to 1.
0.
Make sense?
Wait.
Yep.
Oh, yeah, okay. Yep.
So there we go. We took our functions. Since the domain wasn't explicitly given, it was using what's called the natural domain. And then here is our range. Our big Y is always all the real numbers. Our range is just a set of Y that we actually use. Make sense?
What do you mean by actually use?
So this function never spit out a -1.
Yeah.
So that's not in our range.
Oh.
It's still
Oh.
The range
That
are
use.
the values that we can only actually get to come out of the function.
Yeah.
Okay? Domain, everything we plug in. Range, everything we can get to come out. Make sense?
Yep.
Okay. Next, the graph of a function. If f is a function on some domain D, then the graph of f is a set of all the points x together with f of x for every point in D. So we take that set of points for every point in the domain, and then we plot them in the Cartesian plane. And that's the graph of the function. Almost identical to what I told you guys last week.
That's the Cartesian plane, right?
The Cartesian plane is the xy plane. It's what we graph everything on.
That's strange. I've never heard it called that.
Okay, so let's look at one. So we're going to graph y equals x squared. This time I'm telling you exactly what the domain is. On -2 to 2. That is our big D. That's our domain. Make sense?
Yep.
Now we're going to graph the function on this domain. Now, you're going to do this the way you know in log. You're going to create one of these little T charts with some x values, some y values, plot some points, and then you're going to assume the function behaves nicely in between those points.
Yeah.
Okay, so what does -3 go to on this function?
Why would you do that? Your domain is negative.
Bad question.
That's not on the domain.
It's not in the domain. What are you doing to me? What does -2 go to?
4.
4. What does -1 go to?
1.
1.
What does 0 go to?
0.
What does 1 go to?
1.
2?
4.
3?
Nothing. Third.
Bad question. Okay, so then we plot those points. So we got 0, 0, we got 1, 1, we've got 2, 4, we got -1, 1, and we've got -2, 4. So those are some points that we discovered are in here. Now we're not going to find all the points in there because there's infinitely many. I'm not going to plot infinitely many points. So we're just going to discover a few, and then we're going to assume, and it behaves nice.
Why wouldn't it ever behave not nice?
There are very strange functions out there.
That
That
behave
behave-
though. It has to follow that function, doesn't it?
Well, we're just assuming it behaves nice. What's your argument for it should behave nice? You don't get to say, it's this way, prove me wrong. You have to prove why that's right. I'm going to say, there's a purple elephant in the center of the sun. Prove me wrong. You have to start with, how are you justified in even saying that?
Yeah, I know. I'm
So
saying,
we just assume it behaves nice. We will justify that throughout this course.
Okay, I'll wait for that.
Okay, next, vertical line test. The vertical line test, Author wanted to do this with this figure. Let's really quick plot this shape right here. X squared plus y squared is equal to 1. So
Circle right.
we'll go ahead and we'll pick some points and we'll plot it. So we'll do when x is 0, we'll see what our y is. So if I plug in 0 for x, what do I get?
Do that.
0.
0.
Nope.
0.
When I plug in 0 for x, I get y squared plus 0 is equal to 1.
Right.
Take the square root of both sides, and I get y is equal to plus or minus the square root of 1, which is equal to plus or minus 1. So when I plug in 0, I get two values out.
Which is not a function then, right?
So it's not a function. So you already know this isn't a function. So when we plug in 0, we got plus or minus 1 out for there. So we'll put plus 1 up there, minus 1 up there, 1 to the right, 1 to the left. So we got this point and we got this point. Let's plug in 1 for x. What do we get? When I plug in 1 for x,
You get 1.
then I get y squared
Plus 1 equals
plus 1 is equal to 1. You with me?
1. Yep.
Yeah.
Subtract 1 from both sides, and I get y squared is equal to 0, or in other words, y is equal to 0. So when x is 1, y is 0. So there's a point. Let's plug in negative 1 for x. What's negative 1 squared?
Still one.
1.
1. Y squared plus 1 equals 1.
So
Subtract 1 from both sides, and we get 0 still. And then if we went through carefully plotting a bunch of points, we would get, okay, this thing is a circle. Now you already knew that this wasn't a function because we plugged in one value for x and we got two values out for y.
Yeah.
If you can pick any x, let's say that here's our x, and we get two different values out for y, one up and one down, then we know that our figure isn't a function.
Yeah.
So this is what is called the vertical line test. And it's a way from just looking at a function, just by inspection, you can often tell whether or not it's a function. Which is, if I can ever draw a vertical line through it, and it intersects at more than one point, it can't be a function.
Yeah.
Yeah.
So it's a way from looking at the picture to determine whether or not you have a function. So question, is this a function?
No.
No.
No, why not? Vertical line test. Right there. We intersect multiple points, so whatever this x is, must go to three different values.
Yeah.
It doesn't work. But if I get rid of it like that, now is it a function?
Yes.
Yes. Any vertical line you draw through it only intersects at one point. Vertical line test. Pretty straightforward? Okay. Now, piecewise definitions. Give me some space over here. So, oftentimes, I might give you a function that looks something like this. And ask you to find the equation of that function. I'll say that here's the xy. Notice that it would be really hard to find just one equation that captures this behavior.
Yeah.
So instead, what we do is we say, well, I'll give you the function that works for the piece from here to here, and then I'll give you the function that works for the piece here to here. And this one just has its domain, and this one has its domain. And the resulting function is what you get by kind of gluing those together. It's called a piecewise function. I'm going to give you the definition one piece at a time.
But it's still broken though, isn't it? It's not.
No, we connect them at that point. We make sure that they both give us the same value at that point. So where they hook together, they give the exact same value. So it hooks nicely.
Yeah.
So our first example of that is one that you already know and love. It's the absolute value function. Real quick, what's the absolute value of 3?
3.
3. What's the absolute value of negative 3?
3.
3. So you have some familiarity with this function already.
Yeah.
So plotting the absolute value, what's the absolute value of 1?
1.
1. What's the absolute value of 2?
2.
2. What's the absolute value of negative 1?
1.
1. What's the absolute value of negative 2?
2.
Are you
2.
going with 1?
And so your absolute value function, if I can draw it semi-decently, looks something like this, right?
Yeah.
So if you're trying to define this function, it would be very hard to find the equation that just captures that. But it's real easy to find the equation that captures this half, and it's real easy to find the equation that captures this half. So as long as our two equations give us the same value at 0, we can kind of glue them together and get a nice piecewise definition, which is exactly what we do. We say by definition, the absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. That's its exact definition. So we say use this if your number is greater than or equal on this domain, and use this on this domain. So we split our domain into two pieces, and we define a function for each piece.
Why isn't that x equal to 0 either?
Less than or equal to 0?
Yeah.
That doesn't change anything.
So it doesn't matter whether it is or isn't.
It could matter, because your function could look something like this. There's nothing wrong with this function. My line goes along, ends there, jumps up here, doesn't include that point, but runs off this way.
Oh.
That's still a function. And in that case, they don't give the same value at the point there, because they're not glued together in a sense.
Okay. Yeah. That.
So you don't have to have that. In this special case, it wouldn't matter, because they give the same value there.
Yeah.
Okay, so let's try another one now. So here I'm giving you a piecewise definition, and we're going to try and come up with the graph of this thing. So it spits out negative x if x is less than 0. It spits out x squared if x is between 0 and 1, including 0 and 1, and it spits out 1 if x is greater than 1.
Okay.
All right, so let's just plot some points. What do I get if I plug in -3?
You get
For which one though?
3. You get 3.
I plug it into this function. I want to know, we'll scribble it over here, here's my f that we're talking about. What is f of -3? So now notice -3 can only come in one of these domains. It can't be in all of them.
Yeah.
It's only in one of them. So is -3, is that in this domain, or this domain?
Not first one.
Top.
Top one. So this is our output.
Those 3.
Oh.
So we plug out the negative of whatever we put in. What did we put in?
-3.
So what is our output?
3.
-3, which happens to be 3. So our output in that case would be -3, which is 3. So at -3, 1, 2, 3, our output is 1, 2, 3, point somewhere right here.
Yep.
And that works for the same thing. If I said 9, then it would be 9. Like 9 would go down to the bottom one, which is +1. And then
Well, we'll get to that. Let's not do 9 since I saw my picture 1, 2, 3, 4. You want to do 4?
That was
Let's
it.
plug 4 in there. So what's f of 4? So 4, you're noticing, falls into this domain.
Yep.
yeah.
So what does 4 go to?
1.
1.
It goes to 1. So at 4, 1, 2, 3, 4, our output is 1.
Okay.
All right? What's f of -2?
2.
2. So -2 goes to 2. What's f of -1?
1.
1. And you can see now what this is doing on this side, right?
Yeah.
So this -x1, it goes like this, but our domain is everything less than 0. So up to, but we don't quite include 0. So we'll put an open circle there for now.
Oh.
So we've graphed this portion of our function. You see that?
So that left part is for domains, and the right is range.
No. So far, my domain is my x-axis.
Okay.
This portion of the x-axis
Yeah.
maps to this portion of our function.
Okay.
Now I gotta do the numbers between 0 and 1.
Okay.
Between 0 and 1, I use x squared, including 0.
Yeah.
So what is f of 0 in this function?
0.
Plugging in 0,
Zero, yeah.
0's here, so it's 0 times 0, which happens to be 0. Okay, so 0, 0 is on our function, so we can fill in that up.
Okay.
What does 1 go to? F of 1.
1. That's 1.
1 is in this domain, so it goes to 1 times 1.
How did you go to that domain?
So we're plugging in 1.
Yeah.
Is 1 less than 0?
No.
Is 1 between 0 and 1? Including 0 and 1?
Yes, it is.
Okay, so we're in this domain.
Oh, okay. I see.
All right. So it goes to 1 squared.
Yes.
So we got 1 times 1 here. Or 1 squared. 1 goes to 1.
Okay. It's domain separate.
All right, let's try one more. What does 1/2 go to?
Wouldn't it go to the second domain?
It goes into this domain.
That domain.
So the output is
1/4.
1/4. 1/2 times a half, which is 1/4.
Yeah.
It's 1/2 squared or 1/4. So at 1/2, we go up to 1/4. And if we were to carefully plot the points in here, we'd see that this looks a little bit like a parabola on that piece. All right, now let's look at this last piece. What does 2 go to?
2 goes 1.
1. What does 3 go to?
1.
What does 4 go
The
to?
rest of 1.
What does pi go to?
1.
What does the square root of 2 go to?
1.
1. Good. So all the rest of these just go to 1. So there's our function. We just graphed it.
Okay, so I see it now.
Piecewise definition. Okay. Next two functions that we're going to talk about, really simple functions. They're just the floor and ceiling functions, or the round down and round up functions. So if I give you a number and I put it between brackets that only has the bottom bars, not the top, that means round it down. And if it has the bars on the top and not the bottom, that simply means round it up.
Is this used in trig?
Trig? I don't know. They're common
I've
functions.
never
The
seen
floor
this.
function and the ceiling function.
Trig.
Round up, round down.
Huh, strange.
Okay, so what's 2.4 rounded down? Thank you.
That's just 2.
That would be just 2. So you round down to the nearest integer. What's 2.9 rounded down?
2.
2. What's 0 rounded down?
0.
0. What's negative 0.3 rounded down?
0.
Or, negative 1.
Negative 1. You round down
Oh my god.
to the closest integer.
Yeah.
0 is up from negative 0.3.
Yeah.
Okay. What's negative 2 rounded down?
Negative 2.
Negative 2. What's negative 1.7 rounded down?
Negative 2.
Negative 2. What's negative 1.3 rounded up?
1.
Negative 1.
Negative 1.
Oh, yeah.
What's 0 rounded up?
0.
0. What's 1.4 rounded up?
2.
2. Okay, once you get the hang of those, pretty simple. Rounding down, rounding up. Okay, gonna move the camera. Any other questions on stuff on the left-hand side of the squiggly line?
I think we're good.
All right. Pretty good. Good enough. Yeah, I can see all this, so I can use this to scratch space if I need to. Okay, so next. An increasing function and a decreasing function, that's what we're going to define. But already giving you intuition for this, just looking at these pictures. Question, is this function increasing or decreasing?
Increasing.
Increasing. Is this function increasing or decreasing?
Decreasing.
How do you know? The further to the right you go, the more down it is. Right?
Yeah, the actual definition.
Almost. I'm going to give you the exact definition. But that's the intuition behind the definition.
Yeah.
We're just going to use some fancy symbols here. Here's what we're going to say. We're going to say pick 2 points in your domain, call them x1 and x2. Here's x1. Here's x2. Pick them anywhere you want, doesn't matter. The only rule is make sure x2 comes after x1.
Yeah.
So pick 2 numbers out of the domain, whichever one's smaller, call x1, and call the bigger one x2.
Okay.
Okay. If your function is decreasing, notice here is f of x1,
Yeah.
and here
X2.
is f of x2. For this function here, f.
Yeah.
What's bigger, f of x1 or f of x2?
X1.
F1.
F of x1. So your function is decreasing
Yeah.
if f of x1 is greater than f of x2.
Yeah.
Or, to say that different, I think that's the way I say it. And then let's look at this other function. We'll call this one over here g. So here's g of x1. Here's g of x2. Right? What's bigger, g of x2 or g of x1?
G of x is 2.
G of x2. So in that case, the function's increasing. Okay, so now here's your exact definition. Let f be a function on some interval I. So I is your domain.
Okay.
And let x1 and x2 be points in I, such that x1 is less than x2. Pick 2 points out of that interval, call the smaller one x1. With me so far?
Yeah.
Okay. If f of x1 is less than f of x2, then f is increasing. If this one we call g, but if f of x1 is less than f of x2, we say the function's increasing.
Yeah.
Similarly, if f of x1 is greater than f of x2, then f is decreasing.
Is G used as a substitute when you're already using an F and an
Yeah, it doesn't matter what you call it. We typically use f, g, and h for functions.
Yeah. I
But
was just wondering because I said
yeah, standard notation. Okay. So any questions about increasing or decreasing? So a function is increasing if for any 2 points you pick in the interval, this is always the case. Now it always has to be increasing between those points. Or always decreasing between those points. Alright, next we talk about even functions and odd functions. Function being even or odd. So some function f of x is even if and only if f of x is equal to f of negative x. If x and negative x give you the same values, then the function's even.
Even, what does even mean by that?
We're defining what it means for a function to be even. A function is even
Oh.
if and only if f of x and f of negative x give you the same value.
Okay.
So in other words, f at 3 and f at negative 3 are the same.
Which would be a parabola.
A parabola is an example of an even function. Good.
Okay.
And a function is odd if and only if f at negative x is equal to negative f of x. Intuitively, this means it's going to be even means it's symmetric with respect to the y-axis. Odd means it's symmetric with respect to the origin.
So it's like,
If you've got the point xy, you've also got the point negative x, negative y.
yeah.
That's what it's going to mean. Okay, so let's go over some examples looking at these things. So f of x equals x squared. Is this even or odd or both or neither? Even. But let's actually test it. So let's see, when is it even? It's even if f of x is equal to f of negative x. So we got to figure out what f of negative x is in this case. So f of negative x is, I need a plug, we're looking at this function first.
Yeah.
So underline the one that we're talking about. So if I plug negative x into this, what do I get? I get negative x squared. Right?
Yeah.
What's negative x times negative x?
Oh, yeah, positive x, so it is positive.
It's just x squared.
Yeah.
So, which is the same thing as f
Wait,
of
why
x.
is it x squared? If you're, how did you get x squared?
Negative x times negative x is positive x squared. Negative 2 times negative 2 is positive 4.
Why are you keeping the
Square.
yeah, the square?
Because it's still squared. Look, what is negative 2 squared? This is not equal to 2.
Yeah, it's 4, isn't
It's equal to 4. Or in other words, it's equal to 2 squared.
it? Oh, you're just calling it that. Okay, yeah, I see what you're saying.
Negative x squared is just x squared.
Yeah.
Okay. And x squared is exactly f of x. So f of negative x is equal to f of x.
Yeah.
Okay, so this one was even. Oops, didn't leave a place to write what it was. So that one's even. All right, now we're looking at this one. Even?
Yeah.
Again? Let's see. So in this case, we've got f of negative x is equal to what? Negative x squared plus 1, right? But negative x squared is the same thing as x squared, and we still have our plus 1,
Yeah.
which is f of x. Okay, so it's even.
Yeah.
Oh, sorry, we weren't checking if these things were odd. Let's go back and check if this one's odd.
What do you mean? Check. We know it's even. It can't be both.
Can't be both? Ever?
Probably good.
It probably could. Unless you got a proof for me. I won't just take you saying it as that makes it true.
No,
Okay, so let's check if it's odd.
yeah, check.
So checking this one, we now need to check. So we already found out what f of negative x is. So we need to look at negative f of x. What's negative f of x equal to? What's f of x?
X squared.
X squared. So it's just equal to negative x squared.
Oh, yeah.
Is negative x squared the same thing as x squared?
No.
So then f of x is not equal to f of negative x. We already found out f of negative x is just the same thing as f of x. So this one was not odd.
Yeah.
So it's even, not odd. This one we're going to have the same problem. It's going to be even, not odd. All right, let's move on to this one. X. F of x equals x. So first off, let's look at f of negative x. What's f of negative x equal to?
X squared.
We're doing this function now. Right here.
Oh. It's equal to that. Negative x.
It's equal to negative x. Is negative x the same thing as x?
No.
So this function is not even. Because f of negative x is not the same thing as f of x.
So it's odd.
So it's not even. Does it have to be one or the two? Maybe it's not either.
It's,
Well, let's see.
yeah. It's,
Now let's look at negative f of x. What does that equal to?
Negative x.
negative x. Is negative f of x equal to f of negative x?
Yes.
Here's negative f of x.
Yeah, there you go.
Here's f of negative x. Are those equal? Are those the same?
Yes.
Yes. So it is odd. Lucky guess. Lucky guess. Let's do the next one. X plus 1. So now we're looking at this function. So, what is f of negative x equal to?
Which one?
Negative x plus 1.
Yeah, negative x plus 1.
It's equal to negative x plus 1. What is negative f of x equal to?
Same thing.
That is equal to negative x plus 1.
Oh,
Distribute your negative, that gives you negative x minus 1. Not the same thing. So it's not odd. It's not even because this isn't equal to f of x, and it's not odd because this isn't equal to this. So it's not even, and
What's
it's
the
not odd.
definition for odd again?
Odd, f of negative x is equal to negative f of x. So f of negative x, negative f of x. Those are not the same thing.
So what? Yeah.
So when you took an even function and you added 1 to it, it was still even. When you took an odd function and added 1 to it, it was no longer still even, odd.
Yeah.
All right, let's look at our last one. F of x is equal to 0. Let's see, is it even? So let's see, what is f of negative x equal to? 0. Is that the same thing as f of x?
Yes.
So it's even.
Well,
Now let's look at negative f of x. What's that equal to?
0.
Negative 0, which is equal to 0. So it's odd.
Yep.
So it's even and odd.
But that's just 0.
Still a function.
Still a function. It's just a constant function.
Yeah. But that's-
So we've seen one that's both, neither, one, and the other. Right?
Yep.
Okay. So that's even and odd. Any questions about that? This eraser is so dusty. No other questions?
I think we're good.
Okay, then let's move on now to the equation of a line. You've probably seen this 100 times before, but good for you to see where this comes from at least once. Now, back from your geometry, what's the basic property of a line?
mx plus b.
Well, that's the equation we're going to derive. Let me show you where that comes from.
Oh, it's like mx.
What do we know about every line?
X
Slope.
goes through 2 points.
It has at least 2 points. Every line contains at least 2
Yes.
points. So pick some line. Our job is to come up with the equation of this line. That's what we're trying to do.
Isn't that the slope? Well, no. Yeah. Shoot.
So every line, here's some random line. I'm guaranteed it has 2 points.
Yeah.
So label 2 points on there. x1, y1, x2, y2. You with me?
Yep.
Now pick any other point on the line. Doesn't matter where. I'm just going to draw it where I have space to write. We're going to call that point xy.
Okay.
And we're going to see what every other point must satisfy to be on this line. You with me?
Yeah.
Okay. Now first off, what is the slope of this line right here?
It's
What's the slope of this?
It's a rise and a run.
Rise over run, right?
Yeah.
Let me shift this down a little bit. So this is the point x1, comma, y1. So we need rise over run.
Yes.
What is this distance from here to here?
X.
X2 minus
Well,
x2 minus x1.
what do you get to?
It's this distance minus this, the end. How do you find the distance between any two numbers?
Oh, gotcha. Yep.
One minus the other, you take their difference.
Yep.
Yeah.
What's the difference? How far is it to go from 3 to 10?
7.
7.
How did you do that?
Minus
10 minus 3.
Okay. Yeah.
Same thing. How far is it to go from x1 to x2? You take x2 and you subtract x1. Oh, sorry, x1 right here.
Yeah.
Oh.
So this distance from here to here, the distance at the bottom of our triangle, is x2 minus x1.
Yes. Yes.
And what is the height of our triangle?
Y2 minus Y1.
Yeah.
y2 minus y1. You with me?
Yeah.
y2 minus y1. Okay. Now for our second point that we picked, let's not pick that one. I need the triangle a bit bigger so that we have room to write. So I'll put my xy right here. Now for any other point here, what is its slope? What's the distance from here to here?
X1 or x minus x1.
X minus x1.
And then the same thing.
So this distance is x minus x1. And what's the height?
Y minus 1 minus y. Or it doesn't
Y
matter.
minus y1.
It doesn't matter the order, does it?
Yes, it does. But you can take the absolute value if you want.
Okay.
We won't worry too much about the order though. We'll say we're always picking it right. Okay, now notice that any point on the line has to have the same slope as every other point on the line.
Yes.
In other words, the slope of this triangle has to be the same as the slope of this triangle. Because they're both on the same line. Make sense? Okay, so that's a basic fact that you use to go from here. So let's look at the slope to this point. It's its rise over its run. So it's y minus y1 over x minus x1. That's the slope between these 2 points. And it has to be equal to the slope between these 2 points, which is y2 minus y1 over x2 minus x1, right? Now, I'm going to multiply both sides by x minus x1. And so I'm left with y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1.
You multiply both. Oh, yeah.
By x minus x1. So they cancel out over here, and that moves over there. Now, you've most likely seen that equation. That is your 2-point formula for a line.
That
If you know 2 points, this is one of your equations. Sorry, that's a terrible y. That's one of your equations of a line. Now, we like to call this thing right here m, the slope. This was the slope between those 2 points. We often call that m, so the other one you've seen is y minus y1 is equal to m times x minus x1.
This is only for the 2-point line.
So this is when you have 2 points. This is called the point slope form. If you know one point that your line goes through and you know the slope, this will give you the equation of your line. Now finally doing some algebra, I'm going to distribute my m across there and move this to the other side. So y is equal to m times x is m times x. M times negative x1 is negative m times x1. And then plus y1 to both sides, so I'm moving that over. Plus y1. You with me?
Yep.
Now, notice whatever these numbers add up to is what I get for y when x is 0. If I plug in 0 for x, what do I get?
0.
I get y is equal to all this stuff. Negative m times x1 plus y1. Right? We like to call that all that gobbledygook together. We call it b. And what is b? It's the value of y when x is 0. Or in other words, it's your y-intercept.
B is that when it's substituted for 0.
B is what you get when y is 0. Or when x is 0. It's your y-intercept. When x is 0, you get b. So our final form that you know and love is y, or f of x, is equal to mx plus b. Recalling all that gobbledygook, b.
I did not know that.
So then you get y is equal to mx plus b. And that's the one that you all seem to love the most.
Well, it's so much bigger than that.
But so there's your 3 equations. If you know 2 points, you can use that one. If you know point slope, you can use that one. If you know the slope and the y-intercept, you can use that one. You guys all love the slope-intercept form, and so that's one we use the most.
But they all mean the same, right?
They all give you the exact same equation.
So why wouldn't you use that one?
You can use whichever one you want. It's just a matter of what information you have available to you. You use this one if you already know your m and your b.
Yeah.
You know your slope, and you know your y-intercept.
Yeah.
If you just know your slope and one point on the line,
Yeah.
then you would use this one. And if you know 2 points on the line and you don't know your slope, you'd use this one. They're all logically equivalent.
That's strange. Yeah.
Okay, so that's the equation of a line. Now, for functions that represent lines, functions whose represent the equations of lines, we call them linear functions, linear equations. Equations whose graphs are lines.
Straight.
A line. So, if you can write it of the form mx plus b, where m and b are constants, it's a linear equation. It represents a line. Its graph is a line. Right?
Yes.
Yeah.
Okay. Example, f of x equals 2x minus 1. Looking at that, you instantly know that's a line. And what's its y-intercept? Where does it cross the y-axis?
-1.
At -1. And what's the slope?
2.
2. So you're just reading that information straight off. We have a special type of line called the identity function, which is f of x is equal to x.
Okay.
Still a line. What's its slope?
X.
1.
1. This is the same thing as, write it out explicitly,
Oh,
1
nice.
times x plus 0. That's just x. So what's the slope?
1.
What's the y-intercept?
0.
And you know what these things look like, right?
Yeah.
Come back over here, I guess. So, really quick graphing them. This first one, f of x equals 2x minus 1. So across the y-axis at -1, and it has a slope of 2. So if you go over 1, you go up 2. If you go over 1, you go up 2. Right? So that one looks like this. F of x equals x, what does that look like?
Straight line.
That looks like just a line right at the 45, right through the center like that. Right?
Yeah.
Okay, finally, our last type of linear function is called a constant function, which is where f of x is equal to c. Is that a line?
Yes, the same way.
Yes. How can I show out that's a line? I could have just as easily written this as f of x is equal to 0 times x plus c. What's the slope of this line?
1.
0. And what's its y-intercept?
C.
C, whatever C is. So let's look at a concrete case of one like this really quick. Let's look at f of x equals 3. Constant function.
What's the difference between constant and identity?
That's C. So here's identity right here.
Okay.
Our constant function. When I plug in 5, what do I get? 3. When I plug in 2, what do I get? 3. When I plug in 100, what do I get? 3. I get 3 no matter what. So I get a line with the slope of 0, whose y-intercept is 3.
Yep. Oh, yeah.
So constant function is very different from identity.
Yeah.
Identity has a slope to it, namely a slope of 1.
Constant.
Constant function has no slope,
Just the y.
just the y-intercept.
Yeah.
And the function has that same value everywhere, whatever its y-intercept is. Make sense?
Yep.
Okay. Proportional. What does it mean to say that y is proportional to x? It means that there exists some constant k that you can multiply x by to get y. They are proportional, where k is not 0. What's an example?
Well, why can't k be 0? If y is
Because then you're saying y equals 0. And x doesn't have any effect. And so y is no longer proportional to x. Proportional means if I increase my x, I increase my y. And if I decrease my x, I decrease my y.
Yeah, I see that.
That's what proportional means. What are two things that are proportional in our universe?
There's a lot of them. I think of one.
One that might be proportional, how easy a class is and the number of students in it. The easier the class, the more students there are. The less easy it is, the less students there are.
Doesn't proportion have to be exact every time, though?
Well, this would be exact every time. So that was just giving you intuition.
Oh, that's...
If we
that's-
assume we're dealing with an ideal gas, then you can say volume and temperature. If you increase the temperature, you increase the volume.
By an exact amount.
Proportionally with
It
an
doesn't
ideal
have
gas.
to be.
So keeping pressure, keeping the number of molecules, keeping that constant, and assuming it's an ideal gas, yes, you study that in chemistry. And you might have played with this. I don't know if you were ever a kid and took a balloon and stuck it in the freezer. And the balloon shrunk. Pulled it out. As it warmed up, it expanded again. So volume and temperature are proportional.
Okay.
Now we also have the notion of things being inversely proportional. That would be y is equal to some constant over x. This time, as x goes up, y goes down. An example of that might be pressure and volume. If I take a balloon now and I start pulling it down in the ocean, lowering it further and further down in the ocean, the further down it goes, the more pressure there is, the smaller the balloon gets.
Okay, yeah, that makes sense.
So directly proportional, sometimes we call this directly proportional, sometimes we call this inversely proportional. Make sense? Okay. Power functions. What's a power function? A power function is any function in the form x to a.
What's a in this? Just a very
Could be anything. So I'm going to draw out some power functions for you where we pick different numbers for a.
It's exponential, right?
No. It's a power function. An exponential has a conversely. An exponential looks like this, a to the x.
So that's a different thing.
Completely different thing. We'll talk about exponentials over there.
So so I just
Okay, so power function. So what is x to the 0?
0. Oh,
X, anything to the power 0 is 1.
why is that?
Well, we're not going to do that derivation. Right? Give you one quick idea for it. What does it mean to have 2 to the negative 1? You put it in the denominator to make it positive. Are you okay with that?
Yeah.
So this is equal to basically 1/2, right?
Yes.
And what is 2 to the 1 equal to? 2.
2.
So now, if I take 2 to the 1/2 and I multiply it by 2 to the 1, what do I get?
2.
What's 1/2 times 2? What's half of 2?
1.
1. Or what do you get if you have 2 halves? 1.
1.
So, 2 to the minus 1 times 2 to the 1 is equal to 1.
1.
2 to the minus 2 over 2 squared would still be 1. Now you might also remember your exponent rules, that when you multiply terms, you add exponents.
Yes.
So this is also equal to 2 to the negative 2 plus 2, which is equal to 2 to the 0. So 2 to 0 is 1. And I can do it with 3, and I can do it with 4, and I can do it with 10. Okay, there's just some intuition. All right. So x to the 0 is 1. And we're going to assume 0 to the 0 is 1. Because 0 is a very bad point. Okay, so if we graph that, and if this is 1, then that function just looks like this. Right?
Yeah.
X to the 1, or x to the 0.
Which one are we looking at? That one? Okay.
So we're doing the case where a equal
Yeah.
to 0.
So yeah, it'd be 1.
Okay, what about the case where a is equal to 1?
Just,
Then that's just x.
Yeah.
And we already know what that looks like. That's just a line like this. That's f of x equals x.
yeah.
All right, now let's do when a is 2. So f of x equals x squared. What does that look like? A parabola.
Oh yeah, that's right.
All right, what about when we have a cube? Do you remember what that looks like?
Yeah.
This shape?
Yeah.
Something like that. I
Oh.
did an awful over here. It is a function.
It is the same one you
Yeah,
tried
so you
earlier.
get
Oh.
the line.
And then what does a to the 4 look like?
It's a parabola.
It's kind of parabola-ish, but it grows way faster on the sides and it shrinks down way lower in the middle. It looks more like this. And then shoots up.
Which would be the same if it was 8 or 16.
Which would be the same as what?
A equaled 8, it would look the same except for just exponentially go straight.
Except for this would shoot up even faster.
Yeah, that's
Correct. Okay. So now notice, is this function symmetrical with respect to the y-axis?
Yeah.
If I take all these points and flip them over the y-axis, do they just land on themselves again?
yeah.
Yeah, so it's an even function. Notice that this function has symmetry with respect to the origin.
That's odd though.
So it's an odd function. What about this one?
Even.
This one?
On.
This one.
Even.
And that's where they get their names. Even and odd function, it came from looking at power functions and classifying them. So that's where they get their names. Okay, next, polynomials. Oh, go ahead. Oh, go ahead. Next, polynomials. A polynomial is any function that can be expressed this way. Now, okay, there's a whole ton of symbols there, so let's consume this. It can be written as some constant times x to some whole number, maybe 5, plus some other constant, maybe the same or maybe different from that, times x to, now the 4, plus dot 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 times some constant times x squared, times some constant times x to the 1, times some constant times x to 0.
What is that n?
N. So any n. Pick any n you want.
What does n stand for?
Any natural number. If your function can be expressed this way, if I can find an n for your function so it can be expressed this way, then your function is a polynomial.
Is there a second?
Let's do some really simple examples. Is this function a polynomial? 2x minus 1. The answer would be yes. What is our n in that case? 1.
How do you determine that?
So this function can be written as 2 times x to the 1 minus or plus negative 1 if you want. So there is some n I can find that makes it follow this pattern. In this case, the n was 1, so it's only to here. Sorry, put a 1 right there to help you see the pattern. Let's do another one. Is this one a polynomial function? 3x cubed plus 9.
I would assume yes, because 3 can breed an n in the x.
Yeah, it can be expressed as some constant times x to 3 plus some constant times x squared plus some constant times x plus some constant. Right?
Yes.
3x squared plus 9.
Yeah.
Good?
What is that? I'm so confused. What is that huge long?
This thing?
Yeah, what is that?
This is just showing you the pattern. It can be expressed as x to some integer,
Okay.
some whole number. In this case, it was 3, starting at 3.
Yeah.
So you have some number times x to the power of 3, plus some number times x to the power of, what's 3 minus 1?
2.
2, plus, dot dot dot, 2, 1, 0, all the way down. So counting all the way down.
Oh, I remember this.
So your exponent is just decreasing by 1 each time.
Yes, I
So
see.
it starts out as some positive whole number.
Yeah.
Maybe 10, maybe 50, maybe 3.
Yeah.
And then you can keep counting down, finding constant terms to multiply by each one. If it can be expressed that way, it's a polynomial.
Yeah, I see that.
Let's do some more examples. Is this a polynomial? 2 times the square root of x.
No.
No, because the square root of x, what is that as an exponent? That's x to the 1/2. Our exponents have to be whole numbers.
Yeah, that's not.
Counting down. All right. What about 6 to the x?
That is.
Our exponents have to be whole numbers. That's an exponential function. It's not even close to a polynomial.
Well, yeah, because you don't determine x, but if x was a value, then it would be.
No, it's a function. X isn't a constant, it's a function. I get to plug in all the x's I want into that.
Oh, yeah, because x makes it a function.
All right, what about this? Is this one a polynomial?
No, because you can't express 7.
Why is it 7 just x
Or,
to 0?
no, yeah,
It's a polynomial.
it is.
Yeah, it is.
Yeah, it is.
Because you can express it.
Yeah, it is.
Plus 0x
Those x's
7
you
plus 0x6 plus 0x5 plus 0x.
Yeah, you just do your zeros for all your other terms. So some constant times x to the 10 plus some constant times x to the 9 plus some constant times x to the 8 plus some constant, namely 0, times x to 7 plus some constant, namely 0, times x to 6, 0x to 5, 0x to 4, 0x to 3, 0x to 2, 0x to the 1,
Yeah.
7 times x to 0 if you want to think about it that way,
Yeah.
or just your last constant. We don't bother putting times x to 0.
That makes sense.
All right, let's try this one. is this polynomial? I have pi x squared minus the square root of 2. Is that a polynomial?
Yes, that is. Yes.
Yeah. You got your two constants?
Yeah, I've got some constant times x squared plus some constant 0 times x plus some constant negative square root of 2. Constant times x squared plus constant times x plus constant. It works.
Yeah.
So if we can express it that way, it's a polynomial.
Yeah.
Yeah.
Make sense?
Yeah.
In short, a polynomial is what you're going to have if all your x's are the whole numbers, positive whole numbers. Maybe try another one. Is this a polynomial? We'll say 3x squared minus 7x squared plus 1.
No.
No.
Is that a polynomial?
Wait.
Now what did I just tell you? I told you if all your x's are the whole numbers, your
Yeah.
whole positive numbers, you're pretty much guaranteed it's a polynomial. In this case it is. Because we can now re-express that as,
That's
see if I can get this to perhaps just even worse.
Negative 4x squared.
We can re-express that as, let's see, 3x minus 7x, that's negative 4x squared plus 0x plus 1.
Yeah.
This is the same thing as that. If it can be expressed in this pattern, it's a polynomial. Intuitively, if all your exponents are to positive whole numbers or to 0, then you've got a polynomial.
Gotcha.
Because then it can be expressed this way.
Yeah.
Okay, any other questions on that? Before we move to the other board?
Sure, we'll have some when homework comes.
All right. I sure hope you do as well. That means you're doing your homework. All right. How far back can I go? Oh, wow, that's why. Okay, I think that's got the whole board. All right. Next, we move on to rational functions. What's a rational function? F of x is a rational function. Is a rational function if it's equal to p of x over q of x, where p of x and q of x are both polynomials. So a polynomial over a polynomial is a rational function. Question: is this rational?
No. Wait.
Can you define polynomial?
Wait.
Polynomial, that's what we were just talking about over there.
Oh yeah, that is.
Function's a polynomial if it fits that pattern. Or in other words, it's a polynomial if all your x's are to positive whole numbers or 0. So is this a rational function?
Yes.
Yes.
Yes, because we have a polynomial over a polynomial.
Oh yes.
Is this a rational function?
No. Oh. No.
Prove it, Joe.
Yes.
No,
No, because x, the square root of x can be represented as x to the power of 1/2. That's not.
Oh yeah.
Right, here's your problem. Square root of x. You can't have the square root of x. That's the same thing as x to the 1/2. All our exponents have to be positive whole numbers or 0.
Right.
Okay, that makes sense. Yeah.
Think you got it?
Yeah, I think I do.
All right, let's try another one.
Yes.
Yes.
Is that a polynomial?
No, it's not.
No, because x is a function, meaning it can be in.
That's
That is not a positive whole number.
Yeah.
That's our variable.
Yeah.
No.
Yes.
Yeah.
No.
Yeah.
Another way you might want to think about it is the type of equation you want to see show up on your homework. You like polynomials. They're nice.
Yeah.
You don't like dealing with square roots. You don't like dealing with exponentials. You don't like dealing with logarithms.
Yeah.
You like it nice and pretty. Okay, so that's rationals. Now we're moving on to exponentials. An exponential is written as a now to the power of x. Notice your variable is in the exponent now.
Yeah.
So this isn't x squared, this is 2 to the x.
Yes.
Let's just make sure we understand very concretely the difference between those. Let's look at f of x equals x squared, and f of x, we'll call the next one g, and g of x is equal to 2 to the x. Question, what is f of 10?
100.
It's equal to 100. What is g of 10?
2, 4, 8, 16, 32, 64,
Something.
128, 256, 1024, something like that.
1024. Or in other words, it's 2 times 2 times 2 times 2 times 2, 10 times.
Okay.
Exponentials grow way faster than power functions,
Yes. Yes.
right?
Yeah. So.
You plug in 20 up here, you get 400. You plug in 20 down here, you're getting well over 1,000,000.
Yeah.
You plug in 30 up here, you're still under 1,000. You plug in 30 down here, you're now well over 1,000,000,000.
Gotcha.
20.
Are you?
10 to 20.
30, you're well over 1,000,000,000. Yes. Think about it. 2 to the 10 is this. What's 2 to the 10 times 2 to the 10 times 2 to the 10? That's 1,000 times 1,000 times 1,000 plus change. 1,000,000,000 and change. Right?
Yeah, that's right.
Okay. So, that marker's kind of up. So, exponential functions, not a power function. So, f of x equals a to the x, where a is some number greater than 0 and a is not 1. Why don't we want it to be 1?
Because then it doesn't grow.
What's 1 to the x? It's 1. Then it's just a constant function.
It doesn't grow.
It's not a power function, or it's not exponential. You just wrote 1 in a fancy way. Okay. So,
You can't have negatives for a.
you can't have a as a negative number.
Wait, why?
Because a squared.
Try and calculate this for me really quick. Do negative 2 to the 2.5. You'll realize real quick you don't have the tools to do that. And you don't know how to work with that.
Calculators could do that, right?
Plug it in, see what you get.
Flying calculator.
Right here.
What was it, negative 2?
And there's no erase on there. Sure.
Yeah. About negative 5.6, and then it goes on to that.
And how's it coming up with that?
So there's probably square root, there's a square root in there somewhere.
In fact, what you might be interested in looking at is negative 2 to something like 3.9, and then go look at negative 2 to the 4th and see the values that those give you. And your intuition might tell you that those should be pretty close to each other.
I don't think they are, but sure.
Oh, I'm done.
It's just error domain.
Let's see, correct. That's not right.
Oh, did you do 2 to the 2.5?
And then negative that.
And then negative that? I bet that's what you did.
I'm trying to
Yeah, it
graph
just
it.
says there's an
Okay.
error.
That's the graph of it.
So,
That's strange. It seems like that should be something you could do.
Yeah, right.
there's ways to work with that. The point is, you don't automatically have those tools. And it's not
So
as trivial
you can.
as you might first think it to be.
You can, it's just not practical.
It's not useful.
No, it's just not trivial. Okay. So, because we're going to now graph these things. Well, for positive numbers. Negative numbers, they're trickier. And you gotta be comfortable with complex numbers before you can talk about them. That's essentially why. Okay. So, dealing with positive numbers here, let's look at their graphs to get a feel for how these things grow. Alright, so we're going to start with y equals 2 to the x. And we're going to look at its domain and its range and plot some points.
Okay.
So first off, let's start with the easiest one. What's 2 to the 0?
0.
1.
1.
So we know it goes through 1, so it has a point right there. Maybe we'll do the 1 up a little bit higher. So put the 1 right there. Goes through a point right there. There's our 1. Alright. What do I get when I plug in 1? 2. What do I get when I plug in 2?
4.
4. What do I get when I plug in 3?
8.
8. So we're quickly shooting up, right?
Yeah, we're shooting this.
Okay. Now plug in -1. What's 2 to the -1?
One.
1/2. Right?
Yeah.
Flip it down to make your exponent positive. So that's 1/2. If we go to -1, we got 1/2.
To make your exponent positive look like.
So what's 2 to the -2 equal to? Well, that's 1 over 2 to the 2 is equal to 1/4. Right?
Oh yeah. You
Okay,
can't do
now
that.
you're
That's
seeing it.
Tricky. Yeah.
What is 2 to the -3 equal to?
1/8.
3, we get an 8 there. 1/8. And now you see that this is coming down and it's hugging this line. Right?
Yes.
Question. What are all the numbers I can plug into this function? What's our domain? What are all the numbers I can put in there without breaking it?
Everything was 0.
No, we plugged in 0. We plotted that.
Oh.
There she is.
Everything.
Everything. So we can put in everything. All of R. What's our range? What are all the numbers we can get out?
All of positive are.
What about 0?
Oh.
Why can't we get 0?
Because it'll approach it, but it'll never hit it.
Yeah, it will get closer and closer. Pick any negative number you want there, however massive. We're just going to get out a really, really teeny tiny fraction. We never actually get out 0.
Yeah.
We got a half, a fourth, an eighth, a 16th, a 32nd, da 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 da. Keep going down, you get smaller and smaller numbers, but you'll never get so small that it's 0.
Yeah.
So it never quite reaches 0. So our range is everything from 0, not including 0, to infinity. Right? And now let's look at 2 to the -x.
Okay.
Okay. Plug in 0, what do we get?
1.
1. Okay. Plug in 1, what do we get?
2.
No. 2 to the -1 is
Oh yeah. 1.
1/2. Plug in 2, what do we get? 1/4.
1/8. 1/16.
1/8, 1/16, da 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 da. Okay. Plug in -1, what do we get? 2 to the -1.
Reverse.
We get 2.
And then
Plug in -2, what do we get?
4.
4. And then 8 or whatever. And so you see that making that negative just flips it about the y-axis. So 2 to the x is that, 2 to the -x is this just flipped, reflected over the y-axis.
yeah.
Make sense?
Yes.
Okay, those are your exponentials. Now, logarithms. Who knows what a logarithm is?
Okay, hold on.
Back in the middle of this.
So if I know that a to the b is equal to c, this is logically equivalent to log base a of c is equal to b. Logarithms give you exponents. These are inverses of each other. The same way that division undoes multiplication, subtraction undoes addition, logarithms undo exponentials.
What about roots? I thought roots were the opposite of exponential.
Yeah. That's true.
Exponential function, where we're dealing with the exponent. Let me give you an example. So if let's just get comfortable calculating some logs really quick. So we'll do log base 2 of 8. What we're asking is, what exponent do I have to raise 2 to get 8?
Oh, right.
Wait, reset that.
What exponent do I have to raise 2 to get 8?
3.
2 to what power gives me 8?
3.
3. So that's log base 2 of 8. Why? Because 2 to the 3 is equal to 8. If a to the b is equal to c, then log base a of c is equal to b.
Yeah. Calculators do this, right?
Yes.
Yes, calculators can do this.
How?
So now here's what I mean by logs undo each other, or logs undo exponents. If I have log base 2 of 2 to the 3, what is that equal to?
What do I have to raise 2?
2 to the 3 is 8. What do I have to raise 2 to get 8?
3.
3.
That equals 3.
And in general, log base a of a to the x is equal to x.
Yeah, but that.
Similarly, we won't prove this, but just so you know it, if we instead had how would I want to write this? A to the log base A of x, this would also be equal to x. So it's where we're dealing with the actual exponent. What you were thinking about is x squared times and then square rooted or something like that.
Yeah.
Which is when we're dealing with power functions, not exponentials.
Okay.
Okay,
Gotcha.
so power functions and undoing power functions, that's what radicals give you. Now we're talking about exponents,
And next question.
we're talking about exponentials and logarithms.
Okay.
Make sense? So notice where the x is in both these.
Oh.
Okay. So that is a logarithm. Let's just do a little bit more practice. What is log base 2 of 16 equal to? 4. What is log base 3 of 81 equal to? Oh, come on. You know 81 is 9 times 9. And you know 9 is 3 times 3.
3. 4.
4 of them.
Oh.
It's 9 squared times 9 squared.
Yeah.
Or 3 squared times 3 squared.
Yeah.
Okay, let's try another one. What's log base 5 of 125?
No.
2. No, 3.
3. 5 times 5 is 25 times 5 is 125.
Huh. Yeah.
Okay? Getting comfortable with it a little bit?
Yeah.
Okay, so now let's look at a logarithm function. A logarithm undoes a radical or undoes an exponential. It's going to be the inverse of this.
So it's the negative axis or?
Well, let's just make sense of it for a second.
Yeah.
We can play with it. We can figure this out. Log base 2 of x. We're just going to plot some points now.
Okay.
So let's start by plugging in 1.
It's a 0 first.
Let's 1's a perfectly fine one. So 2 to what power gives me 1?
0.
0. So at 1 we get 0. Notice that here at 0 we got 1. At 1 we get 0.
That's yeah.
Right? Next, let's plug in 2.
1.
Then we get 1. Right? What do I have to raise 2 to get 2?
1.
1. So notice here we had 2, 1, and up here we had 1, 2.
Oh yeah.
Okay. Now, plugging in 3, that's going to be hard because we're going to get some fraction. Can't do that in our head. But 4, we can do 4. 2 to what power gives me 4? 2. So at 4 we get 2. So 1, 2, 3, 4. We got 2. All right. What do I get when I plug 8 in here?
3.
3. And what do I get when I plug 16 in there?
4.
4. So I have to go clear out the 16 to find the gap to 4. So in other words, this function is growing stupid slow. Right? This one had 3, 8 because, or this one had 8, 3 because this one had 3, 8. It's going to be the inverse of this thing up here.
Yeah.
All right, let's plug in 1/2. What's log base 2 of 1/2? What exponent do I have to raise 2 to get 1/2?
2.
Negative 1. What's 2 to the negative 1? 1/2.
Oh yeah, it flips. That's right.
It flips. So at 1/2 we got negative 1.
Yeah.
At 1/4, what would we get?
Negative 2.
Negative 2. So at 1/4,
Oh yeah.
we get negative 2. And at 1/8 we get
Negative 3.
negative 3. And at 1/16 we get,
Negative 4.
and now you see this thing just shoots down. What about 0? 2 to what power gives me 0?
It never is 0.
It never gets 0. There is no exponent.
Yeah.
So what was the domain of this function?
The domain?
The domain. What are all the numbers we can plug in?
All numbers greater than 0.
Anything?
All real numbers greater
The
than
domain was 0 to infinity,
not including 0.
not including 0. We also can't plug in a negative number.
Yeah.
I can't do -2. There's nothing I can raise. Oops. I can't plug in -2. I can't raise 2 to some
Yeah,
power and get
yeah.
-2 out of it.
Yeah.
Okay, so our domain was that. What is our range though? What are all the numbers we can get out?
All numbers.
All.
Anything.
Except for,
All real numbers, eventually. This function grows stupid slow, but no matter how big of a number you pick, it eventually gets there.
but not 0.
It gets 0.
Oh,
It
zero.
spits out 0 at 1.
Right.
Oh, yeah.
How?
What's the range? The up and down.
Yes, correct.
It will always reach up. It's slowly rising.
It's slowly rising. This is an increasing function.
Well, if you have infinity going up and it's going over, slowly going up, then
It'll still fill the entire.
Pick any number you want. It will eventually get there.
eventually, how? Because
Huh?
the numbers are growing infinitely faster than.
This is constantly going up.
Yeah, and then there's.
It will
constant-
eventually get to whatever number you choose. Pick any number you want.
8 billion.
8 billion. There is a number I can find big enough such that when you take its log, you get 8 billion.
Yeah. Yeah. That's right.
It just grows really slow.
It's arbitrary.
Yeah. Yeah. It's,
Logs grow extremely slow. They are very slow growing functions.
well, the problem is they grow slower every time you go higher.
Yes.
So.
So they grow slow, and they are constantly getting slower as they grow.
But there's never.
Meaning
fucking
it's
next
how
The
can it
slope
ever-
is constantly decreasing.
It won't ever stop them.
Yeah. I know you're right. I'm just trying to think. You're,
It's not at all intuitive
yeah.
that this thing wouldn't cap out. But it doesn't cap out.
And it exponentially increases on the negative side, right?
Yeah.
Oh, you're saying how fast it drops down?
Yeah.
Sure. Yeah, it's dropping down very quickly. Yeah. But its growth is very slow. Okay. That was logs. We did that, right?
Yes.
Okay. Graphing sine and cosine now. So graphing sine and cosine. Let's graph these two.
On the Cartesian plane?
Yeah. So here we've got 1, -1. Notice that sine and cosine, what do they give us? What does cosine give me? Definition of cosine.
X.
Gives you
It's the x coordinate on the unit circle at that angle.
Oh.
What is the biggest your x coordinate can ever be? 1.
On the unit circle.
On the unit circle.
Yeah. So
The furthest right you can possibly be is 1. What's the furthest left you can possibly be?
one. Negative one.
-1. So cosine can never be bigger than 1, and can never be less than -1. Same thing with sine.
Only on the unit circle, though, right?
They're defined on the unit circle. That's where their definition comes from. What is a cosine? It's the x-coordinate on the unit circle of that angle. That's its definition.
Yeah.
You say, yeah, on the unit circle. Yeah, where it's defined, that's how it behaves. Yes, where it's defined, that's how it behaves.
We'll go through other examples.
So, we're going to graph these things. So, what is a cosine at 0? What's your x-coordinate at 0 degrees?
1.
What's your x-coordinate at 0 radians? 1. You guys are in trouble. You got your test coming up.
The
Cosine of 0 is 1.
The unit circle test.
Yes.
Isn't that memorization?
Yes. You should have memorized these values.
Well, I can do them.
Check. I can take it.
Okay.
Go by value.
So, we're focusing on cosine first. We're going to graph cosine then sine. All right. What was the cosine at pi halves? So notice that we're counting by pi's here. So 0, pi, 2 pi. So here's pi halves. What's cosine at pi halves?
0.
What's your x-coordinate at pi halves? X-coordinate 90 degrees. 0. What's your x-coordinate at pi?
Negative 1.
-1. What's your cosine at 3 pi halves?
0. Or, yeah.
3 pi halves, that's the bottom of your circle.
0.
0.
But that's like, yeah, you're right.
What's your cosine at 2 pi? Once you've gone all the way around the circle.
1.
We're back to 1.
Yeah.
You with me? Let's go back some. Let's instead look at cosine at negative 90 degrees. Negative pi halves.
It'll be
So now we're back at the bottom of the circle.
0.
Right? 0. What's your cosine at negative pi? So we go backwards pi. to the other side of the circle?
It's -1.
Negative 1.
Negative 1.
You see it?
Yeah.
And if we would carefully plot all these values, then we would see something that behaves a lot like this.
It wouldn't be round though, would it?
It would.
It would be close to what I'm drawing.
It's a sine wave.
Well, it's a cosine wave.
Sorry.
And that's what it would be. So at pi fourths, it's root 2 over 2, which should be 0.7 and change. So it should have been
Yeah.
0.7 up.
Yes.
Okay, I see.
Where over here at 3 pi fourths, it should have been negative root 2 over 2, which is roughly negative 0.7.
Yes.
Not quite negative 1, a little bit higher than that. Right?
Yeah.
So there's your cosine function if you were to plot it out. And it keeps going on. We can keep plugging in as far as we want, and it will keep doing that wave forever. It's cosine wave. And that's why we call it a wave function.
A wave function.
Yeah. It sits there and it repeats over and over again. After this piece right here, it just repeats that over and over again. Or after this piece right here, it just repeats that over and over again. Okay, now let's do sine. What is the sine at 0?
0.
0. This is for y, yeah.
0. The y coordinate at 0 is 0.
Yeah.
What's the y coordinate at pi halves or 90 degrees? 1. What's the y coordinate at pi? Once we've gone halfway around the circle. 0. What's the y coordinate at 3 pi halves at the bottom of the circle? Negative 1. And what's the sign back at 2 pi?
0.
0. And once again, the sign now at 5 pi halves, which is the same as pi halves.
1.
We're back up to 1. Or if we would have gone backwards, what's the cosine or what's the sign at negative pi halves? So we drop down to the bottom, then that would have been negative 1. And then what's the cosine at negative pi? 0. And once again, if we would carefully plot all the points, we would see that it looks something like this.
What about
That's your
tangent?
sine function,
Oh, you can't.
which is a sine wave. We will do tangent in 1.3 and secant and cosecant
But you
and
can't turn
cotangent.
it into sort of a wave.
No, tangent isn't a wave.
Tangent is weird, dude.
It looks, yeah, I guess that's all radiant, so.
Tangent looks like a bunch of cubics next to each other, kind of.
Strange, I guess we'll get there.
Yeah, we'll get there. No worries. Okay, so there's your sine function and your cosine function. There's how you graph them. Now notice how closely related those two are. They're almost identical.
Right.
If we took the sine function and we just shifted it back pi halves, we'd get cosine. And this is why sine of theta plus pi halves, if you plus pi halves, it shifts it to the left. If you minus pi halves, it shifts it to the right,
Yeah,
is equal to cosine of theta.
that's very, very interesting.
And you can test that.
So your x and y coordinates will never be more than pi halves away from each other on any given point.
Correct. This point is pi halves away from that point. This point, pi halves away from that point. This point, or sorry, that one's pi halves away from that. That's pi halves away from that. That's pi halves away from that.
Sweet.
Now we'll maintain that. Let's really quick test that. Give me some angle we know how to calculate.
45.
So pi fourths.
Yeah.
So sine of pi fourths plus pi halves is the same thing as sine of 3 pi fourths. And we're looking at cosine of pi fourths. Remember, we plugged in pi fourths for theta. What's cosine of pi fourths? Root 2 over 2. Come on, you guys. You got your unit circle test. You should know it's like the back of your hand by now. You memorized this thing twice.
I memorized it, I just don't know.
You memorized it, forgot it, and memorized it again. You've mastered this. What's the sine of 3 pi fourths? Your y coordinate at 3 pi fourths? Root 2 over 2. He's guessing that I didn't lie to you. Just kidding. Okay. And it happened to work there. But of course, that's the only value it works for. No, it works for all values. We didn't pick a magic point. Okay. But we won't bother testing it any further.
You should though.
And as a counterpart to this, it also means that cosine of, you can do theta minus pi halves is equal to sine of pi, sine of theta. And you can see that from this. Take your cosine function, shift it, pi halves. Oh, did we shift the wrong way?
What?
Sine we want to shift back, green. Okay, green we shift forward. Nope, that's right. Okay.
Doesn't matter. If you shift it forward or back like by halves, it's just
Shift green now, this way pi halves.
Oh.
Yeah, that's dangerous.
Yeah, that doesn't work.
Yeah, it doesn't work. Okay, so have to be a little bit careful there. It's not completely trivial, but shows you a quick way that you can convert between one or the other. There's another way to see that with triangles that I like better that I think we cover in 1.3. But one way to see it from just our graphs. Okay. Next, we're going to talk about combining functions. You're probably already comfortable with this. The notation might look a little bit scary, but the concept is really simple. If I've got two functions, f and g, and I want to add f with g, then that's just f of x plus g of x.
Yeah.
So the function f plus g of x is by definition just f of x plus g of x.
Okay.
Same thing with subtraction, same thing with multiplication, same thing with division. Only thing that might scare you here is function composition. F composed with g of x is f after g of x, or f of g of x.
Yes.
You do g of x first, then plug the result into f.
Yes.
We'll look at examples of all of these.
Okay.
We'll do composition last. So first, let's look at that example I have for you. Here's our f, here's our g.
Okay.
Good?
Okay.
Okay. Really quick. We were like kind of big. Give me a little bit of space here. So this is defined to be f of g of x. I just really quick want you to tell me what is the domain of f here? What's the domain of this function? All the numbers I can plug in there.
It's negative 1 to 1, right?
Can I plug in
We
negative 3?
did this one
We
already.
did it.
It's all numbers below 1, including 1.
All numbers from 1 downwards. You guys see that? The biggest thing I can plug in there is 1. Because now that already gets me to 0. The bigger my x is, the smaller that difference is going to be.
Because you can't
Right.
be negative 2 either.
I can plug in negative 2.
Yeah, because it returns
What's negative negative 2?
positive 2.
Oh,
Positive
you
2.
can't put
1.
2 in there.
You can't put 2. You
Yeah,
can't
that's
put
what I
negative
meant.
2.
You can't
Okay,
put that.
so you can plug in 1 and everything less than 1. So everything from negative infinity to 1, including 1.
Yes.
Let's really quick look at our domain of g. What's that equal to?
All over positive numbers.
Everything greater than or equal to 0, including 0.
Which one are you looking at?
That one.
Oh.
So here are our two functions. Yeah, sorry, forget this other stuff. Oops. Put that line in the wrong spot. But, now let's quickly figure out what f plus g of x is, and then find its domain. So, what's f plus g then?
That's f of x plus
It's
g.
1.
It's just this plus
Back
x. It's just as simple as can be.
Yeah.
It's just the square root of 1 minus x
Yeah.
plus the square root of x.
So it's the square root of 1.
Huh?
It's just the square root of 1.
Because you have to times them can't be right.
Let's put a line right there and drop this down, because I also want to talk about their domains. Now, what is the domain of this function?
Wait, don't the x's cancel out?
No, no, no. There's nothing further you can do with that.
Really?
You're adding them.
Because you're adding the functions. Right?
It's hard to pick numbers that will help you quickly see it because those won't both behave nicely. But no, those do not just
And
cancel
these
out.
can be undefined, right?
What do you mean?
In fact,
Well, that they don't work.
let's pretend that this was a 4 for a second, and then I think you can see it. So now, plug in 4 for x.
Be 0.
So this would be 0, and we'd get 2. Oh, did I give you one that would happen to work? Let's plug in. It's going to behave nicely no matter what I do, huh? Unless we do ugly numbers here.
Don't do another. So,
No, you just can't cancel out those x's.
Is the square root of 1 minus x the same as the square root of 1 minus the square root of x, or negative x? No, it's not.
No. So this is not the same thing as the square root of 1 minus the square root of x.
Right, okay, okay. That's, yep, gotcha.
so what's the
Okay. No, that makes
Does that
sense.
make sense?
Okay. Those are not the same thing.
Okay.
So no, you cannot just combine those.
Alright,
So it's undefined.
what?
No, it's not undefined, it's just that.
Well, what's the domain of that?
Oh, yeah, now what's the domain? What numbers can we
Oh,
plug
I
into
thought
this
that's what
without
we
breaking
were
it?
talking about.
No, we got sidetracked for a second.
Okay.
Alright, what numbers can we plug into there without breaking it?
Any number between 1 and
What's
0.
0 and 1. Yeah, those would work.
You see how he got that?
Yes, it's the overlap.
It has to be the intersection of these two things.
Yeah, yeah.
Because only numbers less than or equal to 1 will work for this piece, and only numbers greater than or equal to 0 will work for this piece.
Right,
Yeah.
right, right.
So it's the one gotcha when you add functions together. It's almost exactly how you expect. The only time students really make mistakes adding functions together is they try to do it on too much of a domain.
Gotcha.
Okay, similarly, let's do f minus g. So we have the square root of 1 minus x minus the square root of x. Pretty straightforward. F minus g.
Yep.
Okay.
What's the domain going to be for that?
Should be.
Same thing.
It'd be the same
Just 0 to
thing.
1.
Yeah.
Good. Okay, let's do f times g now. Square root of 1 minus x times the square root of
It's
x.
the same thing.
Now, with this one, you can combine them in the radical. So the square root of 1 minus x times the square root of x is the same thing as the square root of x times 1 minus x. Or you can say the square root of x minus x squared if you want.
Oh, yep.
So I'm just going to call this the square root of, I'm going to use this version. So this is just the square root of x times x minus 1.
Or x minus x squared.
X.
Did I write it wrong? Thank you. 1 minus x. Good catch.
Oh.
And what's our domain going to be?
Same.
Why can't it be this? Well, plug in 2.
What happens if you plug in 2? You
It's-
make this one negative,
Yeah.
where this one's positive.
Oh yeah, I keep
Which will
thinking
give you a
it's
total
the same.
negative. So you need both these things to be positive, or both of them to be negative. Can you make any number that makes both these negative? No, because whenever that's negative, this is positive.
Right.
But you could do positive though.
So you need them both to be positive.
Yeah.
This is positive, anywhere greater than or equal to 0. This is only positive between 0 and 1. So, it's still the exact same thing. Right?
Yeah.
Now, let's look at the square, let's look at f divided by g. What's that going to give me? That's going to give me the square root of 1 minus x divided by the square root of x. Which you can write all those under the radical, and we can just call this the square root of 1 minus x over x.
Yeah.
And what's our domain going to be?
I feel like it's gonna be the same, but you can't. No, you can't divide by 0.
You can't divide by 0.
So it's just gonna be 1.
So it's going to be 0 to 1 including 1, but we can't have 0 in the domain. And then finally, g divided by f, that would be the square root of x over the square root of 1 minus x,
It would be the same thing though, right?
which is equal to the square root of x over 1 minus x. And what's its domain?
Wait.
0 to 1 without including 1 by including 0.
Include 0, not 1. Good. Good.
Is that going? Are they the same because of the functions you chose, or is that true in general for any function you would choose?
It's almost always going to be the case as just the intersection of what you took. You have to be careful when you're doing division because it could eliminate other points.
Gotcha.
You just can't divide by 0. Okay. Now, function composition. Function composition means you just plug one function into the other function. So, let's do this over here really quick. So here's my f, here's my g. I'm going to look at f composed with g of x. So looking at f composed with g of x. What's that equal to? By definition, f composed with g of x is just f of g of x. So this is just f of g of x.
Yeah.
What is g of x?
G of x.
X minus 3.
Oh.
Oh, there.
It's x minus 3. So this is equal to f of x minus 3. So we're going to plug in x minus 3 into f.
Yeah.
So this is equal to, plugging x minus 3 in for x here, gives us x minus 3 squared plus 1. You see it?
Yeah.
So there's f composed with g of x. Or if we were to multiply that out, let's see, we're going to get x squared minus 6x plus 9 plus 1 is plus 10. Okay, that's quickly doing the algebra. You know how to do that. Okay, now let's look at g composed with f of x. G composed with f of x. By definition now, this is g of f of x. Right?
Yeah. So
What is f of x?
X squared plus 1.
X squared plus 1. Okay, now we're plugging that into g. What is g? It's whatever you give it minus 3. Whatever you give it minus 3. So it's x squared plus 1 minus 3. Or in other words, it's x squared minus 2. Notice that this is very different from this.
Yes.
F composed with g is not the same thing as g composed with f. Make sense? Okay, so this one came out x squared minus 6x plus 10, and this one came out x squared minus 2. So what is happening here is we've got our domain of our function g. We're looking at f composed with g. Which function do we do first? F or g? We do g first.
why is that?
Huh?
Why is that?
So when we do f composed with g of x, that's f of g of x. And so first we plug in for g of x, then we plug into f.
Oh yeah.
What is that doing? That is running x through our function g first to get g of x, and then running g of x through our function f to get f of g of x.
Yeah.
Make sense? And so our inputs that we start out with are the domain of g.
Yes.
Yes.
And the outputs of g, we then have to intersect that with the domain of f, and only those can be fed through f.
Yeah.
So this one happened to be a case where we didn't have any domain problems. Let's really quick look, see if the author gives us an example with domain problems. He does square root of x and x plus 1. So thinking about this again, we're going to do square root of x and x plus 1. Get rid of that, we're just looking at f of g. So f of x is square root of x, and g of x is x plus 1. You with me?
Yep.
So we're looking at f composed with g of x. First off, what is that? That's f of g of x. I guess we'll write it this way first, which is equal to f of g of x, which is equal to plugging g of x to f. With me?
Yes.
Yeah.
Now, what is the domain of g? What is the domain of g equal to? What's everything that we can plug into g?
All real
All real
numbers.
numbers.
All real numbers. What is the domain of f?
All real numbers.
All real plus.
All real numbers.
Including
0 to infinity. So,
Close bracket. Or sorry, not.
yeah.
Bracket.
Oh yeah.
So what is our domain of our whole new resulting function?
It's the intersection between those two. So it's 0 to infinity. Oh,
What do you think?
Anything? Wouldn't it be?
Let's just think, what is the domain of this function?
Like all real. Would it be 0 to infinity?
0 to infinity?
It's -1, including -1 to infinity.
It's -1 to infinity.
Oh yeah,
Nah,
because you can use 0, or you can
Use -1.
square it by 0.
You see that?
Yes. That's
Okay.
weird.
So another place where you're going to get in trouble with composition is looking at the domain.
Okay. Okay.
Yeah.
Okay. Now, last things are pictorial things. Just to give you intuition. Vertical shift, horizontal shift, vertical stretch, vertical compress, horizontal stretch, horizontal compress, reflex across the x-axis, reflex across the y-axis, with pictures. So if I've got some function f of x, in all these cases I'm just going to use x squared because we have a good idea of what that is. So for all these cases, let's pretend f of x is equal to x squared. With me?
Yeah.
Then what is f of x plus k? What does
X
adding
squared
k
plus
to
k.
it do?
You move up on the graph, up on the graph.
Right, it's going to shift it up like that, so it crosses here at k. It's going to shift all your points up k units.
Yeah.
Or if I did minus k, where k is a positive number, that would have shifted everything down k units.
That's only because it's a y-intercept though, right? In the position.
Well, this is no longer the equation of a line. It happens to be giving you the y-intercept.
Yeah.
But don't mix that up.
Yeah.
Just any point. Before, if I plugged in 2, I got 4. Now I get 4 plus k.
Yeah.
So rather than getting 4, I get 4 plus k. I've got to add the k to all my points. All my outputs, I add k to them, which shifts the whole thing up.
Oh, yeah, I see now.
Okay. And similarly, subtracting k would shift it down.
Yeah.
Okay, so that's a vertical shift. Horizontal shift is a bit different. So this time I'm going to look at a horizontal shift. You put your shift inside of the function. So now let's look at f of x minus 2. You with me? Now, just plotting this out, what is that going to give me? It's going to give me x squared minus 4x plus 4. Okay, there it is. Or, if you don't like that, we could just keep it this way. It's going to be x minus 2 squared, right?
Yes.
Let's leave it like that. Let's graph this thing really quick and see what happened. What do I get when I plug 0 into this?
Negative 2.
Negative
0 minus 2 is negative 2. Squared is
4.
4. So at 0, we got 1, 2, 3, 4. Right?
Yes.
Now plug in 1. What's 1 minus 2?
Negative
Negative 1. Squared is
1.
1. Now plug in 2.
It's 0.
0.
0 squared is 0. Now plug in 3.
1
1.
squared is 1.
Now plug in 4.
You get 2 squared is 4.
4.
Now plug in 3.
What?
Same thing you would have got if you plugged in negative 1, and they're both 9. Right?
Yes.
So you get this parabola, but now what's happened with the parabola?
It's got
It was shifted 2 units to the right.
Yes.
So putting a minus 2 there shifts it 2 units to the right. Putting a plus 2 there would have shifted it 2 units to the left.
Yeah.
Make sense?
Yes.
Okay, so that's vertical shift, horizontal shift. Okay, vertical stretch. Why is there no erasers in here? Okay. Let's look at a vertical stretch. So rather than f of x equals x squared, let's look at something like f of x equals 3x squared. What is that going to do to our function? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, whatever. Just drop roughly. So our f of x normally would have looked something like this.
Yeah.
Somewhere here, somewhere here. So our function would normally look something like this.
Yep.
Terrible picture, but you get the idea. Right?
Yes.
Now, what does 3x squared do? So notice 0, plug in 0, we still get 0, right?
Yes.
But when I plug in 1, what do I get?
You get 3.
I get 3. When I plug in 2, what do I get?
6.
12.
2
Oh.
squared is
Yeah.
4 times 3 is 12. So at 2, we're already at 12. So we're way up here. And so you see, it gives us something way steeper. It's like we took that thing and we stretched it up. right?
Yeah.
Same thing.
And if instead I would have done 1/3,
You compress.
then that would have compressed it, and it would have instead looked something like this,
Yeah.
right?
Yep.
So vertical stretch, multiplying it by c, vertical compress, multiplying it by 1/c. Okay? Horizontal compress, squishing it together this way, is kind of going to make it look like it also grows way faster. So horizontal compress, horizontal stretch, I think I did those backwards.
You did.
This should be a compress, this is a stretch. Compress it horizontally is when we multiply it by c. It's going to squish it like this. Let's see what that looks like. So now we're going to look at f of, we'll put the 3x in here. What does that equal?
3x squared.
It's going to be 9x squared, right?
Oh, yes.
And so now, 1 would have normally given you just 1, but now 1's all the way giving you 9.
Yeah.
So if we were to graph that thing, in this case it looks a lot like a vertical stretch with the function that we chose to use as an example.
What is the difference between horizontal compress and vertical stretch?
We happen to pick a function where those look the same.
Oh, but it's not the same for every function.
Yeah.
But it's not going to be the same for every function. That stretching it vertically is the same thing as compressing it horizontally.
Just for even functions or just for this function specifically?
Could you say that for even functions in general? No.
No?
So sine would be a good example. Compressing sine horizontally would look like this.
Yeah.
Stretching it vertically would look like this.
Well, more or less, but yeah.
More or less, but yeah.
And sine's an even function.
And sine, well, cosine's even. So sine's odd. Cosine's even.
Yeah.
So no. Just happens to be the case with the representative function we chose, parabola. And then similarly, dividing it out would have stretched it out this way.
Yeah.
Made it go much slower. Okay, and then finally, these two, the most important, reflecting across the x-axis and reflecting across the y-axis. So let's just redraw our picture. So here's f of x. If we instead look at what would negative f of x be, it would just be negative x squared. What does that look like? That's just a parabola pointing down.
Going down.
So that's how you reflect across your x-axis. Rather than having one that looks like this, you have one that looks like this. So if you multiply the function by a negative, that reflects it across the x-axis. And then similarly, we got to pick a different function now because
Symmetrical.
it's symmetric. Let's pick our cubic. We know what our cubic looks like, right?
Yes.
So our cubic,
Squared.
in general, looks something like this.
Yeah, sure.
So that's x cubed. Let's look now at f of negative x. What does that equal? It's going to be negative x cubed because we have an odd number, so it's going to be negative, right?
That's just gonna go the other way.
And so, yeah, that one's going to look like this.
How is that any different from reflecting? It gets the same. How
So this is reflecting it across the y-axis.
Uh-huh.
Reflecting it across the x-axis is negative f of x. So the cubic happens to look the same when we reflect it across the x or y-axis. You get the same thing.
Okay. Oh. Okay.
Make sense?
Yeah.
So, not picking very good representative functions. Should have just worked with the sine and cosine functions, and then it's real obvious to see what's happening. Well, no, you still have a problem with reflecting them. Yeah. Oh well, it is what it is.
Yeah.
Probably should have just used easy lines. Then it's obvious what's happening. Let's do one more with just an easy line, just to make sure we're seeing it for sure. So, let's pick some line that doesn't go through the origin. We'll say f of x is equal to 2x plus 1. right?
Okay.
So if we want to, just blindly following this, which axis should we flip it across?
X.
X.
The x-axis. So then we're saying that to flip across the x-axis, you do negative f of x, which in this case would be negative 2x minus 1.
Yep.
So let's plot both those lines really quick. Doing it a bit rough. So this one is 2x plus 1, so it's at plus 1. And then when you go up 1, you go over 2. And so very roughly, give you something like that.
Yes.
Reflecting now across the, which one did we do? The x-axis. So we should be reflecting it down here. So then we have negative 1, and now our slope is negative 2.
Right.
If we go back 1, we go up 2,
Yes.
right? And if I did those right, then they would intersect at this point at the same spot. Because if you reflect that point across that axis, it's still on that point.
Yep.
Make sense?
Yes, sir.
Okay, so that's what those are. Any other questions? Got a good feel for it? All right, that took a bit longer than I thought. Okay, so that finishes sections 1.1 and 1.2. Next week, we'll be doing a trig review, and then we'll be done with chapter 1.
Another trig review?
Yeah, the book's version of the trig review, and then we'll be done with chapter 1. Remember, we have chapter tests at the end of each chapter. So pay attention to your syllabus. Tests come fast in this class, because you take a lot throughout the year. Okay. And with that, let's do your